And we're back talking about first law of thermodynamics, continuing on with our discussion there. So we introduced in the last video the first law of thermodynamics. Um, you can see here, this is add the energies in, subtract the energies out. That's going to equal the energy change for our system. Now, what I want to do now is explore these energies just a little bit more. Now, in lecture three videos, we introduced this idea of internal energy. We also reminded us of the idea of potential energy, gravitational potential energy, as well as kinetic energy. We said these were macroscopic energies, the kinetic and potential. They're relative to some external frame of reference. And we said the internal energy is, or we're going to estimate those using properties of our system that we can measure. Let's look at heat and work just a little bit here. Okay, so if we look at heat and work just a little bit, um, so heat, as we mentioned earlier, heat is brought to us by the letter Q. The subscript you see there, 1, 2, that's just meaning that is the amount of heat transfer required to move the state of the system from state 1 to state 2. Notice the lowercase q. As we mentioned in the last video, if I'm talking about the intensive version of a property, then we're going to use a lowercase variable if the extensive version is represented by a capital letter. So capital Q is the total heat transfer. It's dependent on the extent or the size or the mass of the system. The intensive heat transfer, that's heat per unit mass, I could have the same heat per unit mass for maybe a small system with a very, very small mass, as well as a very large system. They could have the same heat per unit mass. It's an intensive property. Joules, kilojoules, or BTUs. We defined last time the British thermal unit, the BTU, also perfectly acceptable. These are all good units for heat transfer. Now, if we a few terms to introduce here. Now, when I give exams in an engineering course, I normally don't have multiple choice or definitions. I do a little bit in, say, an introduction, an intro to engineering course, but once you get into courses like statics, thermodynamics, fluid mechanics, these are normally the courses I would teach. I don't put definitions, true, false, matching questions on an exam. These are their problems. However, you do need to know terminology because the problem statement will be normally a paragraph and it'll say things like an adiabatic closed system undergoes a process where blah blah blah. And so you're gonna have to know what these adjectives mean, right? What is the process referring to? And what is an adiabatic process? What is a closed system, which we've mentioned that one a few times already. But adiabatic process, again, direct quote from your text here because there's no other source. That's a process during which there's no heat transfer. You're in the Changle and Bowles text that we're working out of, they'll say they may call it an adiabatic process. They may just simply tell you the system is well insulated. They may tell you negligible heat passes through the boundary. These are all good ways of describing what could also be called an adiabatic process, where we're going to neglect the heat transfer. You could have, I've definitely seen in some other texts where they'll say the process occurs rapidly. Um, the idea there is if a process occurs rapidly, that means there's not sufficient time for a process to for heat transfer to kind of catch up and get the system back to some equilibrium. Your text in the Changle and Bowles text, I've not seen them use that, but I have seen other texts where they'll say the process occurs rapidly or process occurs over a very short time. And when they use those words, there are some texts that want you to assume there's no heat transfer. Okay. Not something I will use because your text doesn't use it, but that is in the realm of possibility if you're looking at other things. As I mentioned day one, or when you guys were watching lecture one with me, I'm going to assume you've had single variable calculus. So derivatives and integrals in one variable should not be a problem. With that said, we're not going to do any, for me, when I teach, in these type of courses, I don't like to do any crazy integrals. No trig substitution probably ever, and probably no integration by parts ever. I doubt you'll have to do a substitution. Normally, it's just polynomials or kind of the main integrals we might need to do, but I need you to be good at them and quick at them. Notice the dot above the Q here, right? That's something we mentioned in the last set of videos. A dot above a variable tells us what? If you don't know, pause, go back and review your notes. You need to know, what does a dot above a variable tell us? Go ahead, figure that out. Okay, got it? A dot above a variable means it's per unit time. It's a rate. So Q dot means that is the rate of heat transfer, heat per unit time. If I need to know how much total heat has occurred, I need to be able to integrate that heat with respect to time. And if Q dot is constant, integrating a constant is the easiest integral, in my opinion. I think that's a fair thing to say. Integrating a constant is the easiest integral. If I integrate Q dot with respect to time and Q dot is constant, well, Q dot comes out of the equation, or out of the integral, I should say, comes out of the integral. Now I'm just integrating dt. Well, the integral of dt is just delta t, or just t, and I'm going from t1 to t2, that's delta t. So here, that's what you see here. So I've got Q dot times delta t. So if Q is a function of time, to find the total amount of heat transfer, I need to integrate that. But if it is not a function of time, if it's just constant, then I just multiply by the amount of time, and that gives me the total amount of heat transfer. I need to check my phone. I'll be right back. All right, so from there, the good news is you guys will go on later and take an entire course in heat transfer. Most of us will. Not everybody. Not, it depends on what your major is, but most of you will go on to take a course in heat transfer where they are going to spend a lot of time talking about different ways of estimating and approximating, calculating a specific amount of heat transfer. For us here, we're not armed with that information yet. That's a course that is normally has a prerequisite of differential equations, so higher level calculus for that. We're not quite there yet, so you might be. But that doesn't mean we can't have some basic understanding of how heat transfer occurs. So the three mechanisms of how heat transfer occurs. Um, heat can occur in one of three ways. Conduction, that's where you have heat moving literally from one molecule to the next, right on top of each other. So this one's excited and it bumps up against the next one, and that gets both of them excited. And this one bumps up against the next one, and that gets them both excited, and it moves from one to the next. That is conduction, where you have direct contact of a hot object to cooler objects, and that hot object is directly transferring heat from one to the next. The terrible joke I always tell here is that I think about that like the drunk guy in the bar that gets really excited. So if you've ever been to an adult establishment where somebody's had too much alcohol and they get really excited and they start jumping and bouncing around, and that gets the people, if it's packed, that starts getting the people around them kind of excited and they start jostling around. That's conduction. We're moving energy from one excited thing to the next by direct contact. Okay. Convection. What is convection? Convection is the next method of heat transfer. Convection is where I've got a flowing fluid, either gas or liquid. Those are both fluids. I've got a flowing fluid at a different temperature than the object that it's flowing over, coming into contact with. So, if I, in last time we talked about plugging in a fan in a room and that fan blows air, and why does that make things cool down? Well, it's because if you're blowing cool air on you, on your body, that air is cooler than you are. That air is convecting heat. It is removing, heat transfer is occurring by convection when you turn a fan on, one way or the other, whether that's if you're blowing hot air over a cold body, that hot air is through convection is going to add heat, is going to transfer heat to the colder body, and vice versa. If the body, if we're sitting in a cool room, we turn a fan on us, that cool air is going to convect heat, it's going to transfer heat away from our warmer body to the cooler air. Both conduction and convection require a medium, require molecules touching molecules. Radiation does not. Radiation is the third type of heat transfer, and that's basically heat transfer kind of at the subatomic level. If you get an object really, really excited, especially if it's like glowing red hot, if you get metal like glowing red hot, it's emitting radiation, right? And what it's doing is it's emitting highly charged subatomic particles that have lots and lots of energy, and they move away from that very excited body, and they strike those highly charged, highly energetic particles. Then whatever they strike, they're going to impart energy into whatever object it is that they strike. I mean, um, so that is radiation. Radiation can occur in a vacuum. It does not require um, uh, anything in between. It does not require matter to occur or matter in between the two bodies for that heat transfer to occur. The sun right now, you can see it's bright outside my door here, or outside my window here. The sun is emitting radiation on the Earth right now and all the other planets. And there's not much of anything. It's basically a vacuum between us and the sun, but that doesn't stop radiation from occurring. So radiation is the only one of these three that can occur in a vacuum. Okay. And I didn't start a timer, so I'm just going to go with this for a little while and I'll stop it a little bit. It may not be exactly 15 minutes, but we're going to go for a bit. So that's a little bit about heat transfer. Again, know what an adiabatic process is. Know that we don't have to memorize that there's three modes of heat transfer, but that will come up from time to time. But you will need to know what an adiabatic process or what a well insulated means throughout. And all that means is heat is just one method that energy can be added to or removed from our system. Another method that we can add energy to or remove from our system is work. You would have seen work in your physics class, and they may have just introduced work as, I'm going to leave a space in here, work as force times a distance. Right? So I'm leaving spaces in between these variables because that's not the complete story. In the simplest form, this is true. Force times distance works if the force is constant. However, if that force is variable, you need to take the net result of the force applied through the distance. So it's actually the integral of force with respect to distance. Um, if you put a dot above the W, a dot above work, that is power. Normally, we reserve the term power for a work rate. I'm not going to mark you wrong if you call any energy per unit time, any energy dot, if you call any of those power, I wouldn't count that wrong. It's a bit of a technicality, but in general, we try to reserve the term power specifically for W dot or work rate. Power is going to have units of watts or kilowatts, or in the imperial/English system or the American customary, whatever you like to call it, horsepower. Horsepower is also a unit of power. The legend goes that James Watt, who studied steam engines to try to get the most power we could out of steam engines, he was one of many fathers of thermodynamics. The story goes that James Watt figured out that the standard horse or the average horse could lift about 550 pounds of coal at a rate of 1 foot per second using his pulley system to feed his steam engine. So the average horsepower became 550 pound-feet per second. Right? So any unit of power is going to be force distance per time. Okay, what else then? So a little bit about work. There are different types of work. If you're following along in the textbook, as you should be, you might notice the inexact differential, and they'll might take the form of something like this, right? That's technically an inexact differential. Sometimes we'll refer to it as del. It's technically a D. It's just not an exact differential. So you might see del Q or this del W. You might see those from time to time. We're still referring to a differential. Right? And I know not everybody's had a calculus course where maybe you've talked about this. Let's go. Let me change cameras here. Let me kind of define these for you a little bit. Because like I said, I know they talk about this in the textbook. This will be lecture 4, page 1. So just a real quick crash course. There is what we call, just a second. So we were talking about what we call regular or ordinary differential. That is just a regular ordinary D. This is for sure dependent on only one variable. So if I have something that's only dependent on one variable, I would use a ordinary or a regular differential. Now, if I have what we call a partial differential, those of you that have had higher level calculus, you've probably been exposed to the partial differential. Looks kind of like a backwards six, if you will. This is when you are for sure dependent on more than one variable. Absolutely for sure dependent on more than one variable. In your text, when they refer to differential size quantities of heat and work, they'll often use, they may use a partial, but they might also use the inexact differential. So again, I give you kind of the crash course of this because it might be the first time you've seen these, and that's often some version of this. And I think that's kind of about as close as I'm going to get to drawing it that it's going to look. This is maybe dependent on more than one variable. Maybe it's only dependent on one variable. Maybe it's dependent on more than one variable. We don't know for sure. Heat transfer is kind of a good example of that, where heat transfer may only be dependent on temperature and nothing else. It might be dependent on more than just temperature. It might be dependent on the composition of the material. A lot of times, it might be dependent on the shape or the surface area of what it's coming in contact with, for example. So anyway, these are when you see symbols like this in the textbook, and obviously I've drawn those maybe a little bit backwards here. When you see symbols like that in the textbook, that's what they're referring to. I don't, because again, I know there's a good chance that maybe the first time many of you have seen these are just simply referring to inexact differential. It's still a infinitesimally small differential slice. That's really all the D is telling you, whether it's an ordinary differential, a partial differential, or an exact differential. In all cases, we're talking about a differentially small, itty bitty, infinitesimally small slice of these quantities. Okay, so if I've got things like properties, things like pressure, temperature, volume, these are only dependent of this. These are only dependent on the state of the system, the state being one variable. That is the only variable at play. So if we were to talk about a change in pressure, a change in temperature, we'd call these regular or ordinary differentials because they are only dependent on one variable. As opposed to something like heat and work, these are what we call path dependent. That means they're going to be dependent on how you get from one point to the other. The best description I know, or the best solution or way to describe this, is if I'm in a classroom, I like to just grab one of the chairs and just do some work on it, right? Let's say that at state one, we're at some location one, and then I move this chair over here to some location two. That's a property. The location is just a property. The chair doesn't care how it gets from location one to location two. It just knows that it's either in I mean, it doesn't really know. It's not Sinchen, but it's either at location 2 or location 1. So if I were to apply work just like this to get the chair along path A, to get the chair from location 1 to location 2, that's one amount of work, as opposed to if I took the chair around the back of the room, maybe took it out in the hall, drug it along the floor, and then brought it back into the room and plopped it down in location 2, that would be work of path B. You notice that the work of path B is going to be much larger than the work of path A to achieve the same change in properties, to achieve the same change in location. So again, that location is a single variable. It's only dependent on the state of the system as opposed to the work or even heat transfer. They're dependent on potentially more than one variable, but at least one variable, but often more than one variable. We don't know for sure, so we use an inexact differential because we're not sure how many variables are actually at play. We just need to describe the fact that it could be more than one variable. All right, that's a good amount of time. I don't know how long this video is. Again, I forgot to start my clock, but I'll make sure the next one's 15 minutes.